welcome back to Chemical Kinetics lecture series. In the previous class, we discussed about complex reactions and had taken their important characteristics. Today we are going to discuss about classification and derivation of rate law for different types of the complex reactions. So here first one is classification of complex reactions. Classification of complex reactions. Classification of complex reactions. Generally, on the basis of nature of reaction, complex reactions are further divided into 6 types. Their first one is opposing reactions. Second one is parallel reactions. Third one is sequential reactions. Fourth one is chain reactions. Fifth one is photochemical reactions. And last one is surface reactions. Okay, so first one is opposing reactions. Opposing reactions. Second one is parallel reactions. Second one is parallel reactions. Third one is sequential reactions. Fourth one is chain reactions. Fifth one is photochemical reactions. Photochemical reactions. Last one is surface reactions. So this is about the classification of the complex reactions based on the nature. So here first one is opposing reactions. So let us take first type of the reactions now. So first one is opposing reactions. Opposing reactions are, these are also called as reversible reactions. Generally, in complex reactions, in certain cases, products generally revert back together to give the original reactants. Okay, that means initially reactant will give you the products, later that products will be converted back into the reactants. So that type of the reactions are called opposing reactions or reversible reactions. Okay, opposing reactions are reversible reactions. So simply what happens here, all are nothing but the simple reactions only. That means here we have a sequence of simple reactions. Okay, so in this case, that simple reactions takes place simultaneously, but they will be opposites with each other. That's why we are calling as the opposing reactions. Okay, we are calling them as the opposing reactions. For instance, so first one is hydrolysis of esters. Hydrolysis of esters in aqueous medium. Hydrolysis of ester in aqueous medium. So ester is the organic compound. Its general formula is RC double bond OR dash. Okay, so RC double bond OR dash. This R and R dash may be same or different. We don't have any problem. So anyway, it is the organic compound. It is undergoing the hydrolysis. That means reacting with the water. So it is undergoing the hydrolysis and giving the carboxylic acid and alcohol. So carboxylic acid formula is RC double bond OH. So this is the carboxylic acid plus we are getting the alcohol. Okay. So on hydrolysis of ester, it will give carboxylic acid and alcohol. Okay, carboxylic acid and alcohol. So here ester and water are the reactants. They are giving the acid and alcohol. So they are the products. But after some time they will again react together, giving back the original reactants. Hence it is the opposite reaction or reversible reaction. So second example is conversion of nitrogen and hydrogen into ammonia. Conversion of nitrogen and hydrogen into ammonia. Nitrogen and hydrogen into ammonia. Now let us write the reaction. So simply here what happens? Nitrogen will be combining with the hydrogen and giving the ammonia. So NH3, we can get the 2 moles of ammonia. So here it will be utilizes the 3 moles of the hydrogen gas. Okay, so this is the another example for the opposite reaction or reversible reaction. So here also what happens? Reactants are giving the products. Later product is undergoing the decomposition and giving the nitrogen and hydrogen. So in the third case, let us take the conversion of phosphorus pentachloride into phosphorus trichloride. So conversion of phosphorus pentachloride into phosphorus trichloride, PCl3. So write the equation. It is PCl5 will give you the PCl3 plus here we can get the chlorine. Okay. So phosphorus pentachloride will be undergoes the decomposition, will give you the phosphorus trichloride and chlorine gas. But after some time both will be combined together and giving back the phosphorus pentachloride. Hence it is also reversible reaction. And the next one is conversion of ammonium cyanate. Okay, conversion of ammonium cyanate into urea. Ammonium cyanate into urea. So write the formula. It is NH4 CNO. So he is giving the urea. It is NH2 C double bond O NH2. So here also what happens? Ammonium cyanate is undergoing the isomerization and giving the urea. Okay, so after some time urea also again undergoing the isomerization and giving the ammonium cyanate. So that's why it is the example for which one? Opposing reaction or reversible reaction. And the next one is, fifth one is conversion of hydrogen and iodine into HI. So conversion of hydrogen and iodine into HI. Write the equation. It is simply H2 plus I2 will give rise the 2 moles of the HI. Okay, so both will be combining and giving the hydrogen iodide. So later what happens? It is also undergoing the dissociation and giving back the original reactants. Okay, that's why it is also an example for the Opposing reaction or reversible reaction. Therefore, the chemical reactions in which, okay, so here all the chemical reactions, the chemical reactions in which products of chemical change, okay, products of the chemical change react together to give the original reactants. So that type of the reactions are called as opposing reactions. Okay, so the chemical reactions in which products of chemical change react together to form the original reactants are called as opposing reactions or reversible reactions. Okay, opposing reactions are reversible reactions. So here we have in the all the cases we have the two simple reactions. Every cases we have the two simple reactions. So they are undergoing simultaneously but opposes with each other. Okay, so opposing with each other. Okay, so that's why these reactions are indicated by the double-headed arrow. Okay, so that will indicate the chemical equilibrium. Hence, these reactions are generally takes place in chemical equilibrium. Okay, these reactions are generally takes place in chemical equilibrium. So if we observe the 5 reactions, okay, so among the 5, in the last 4 cases, okay, in the last 4 cases, the chemical equilibrium is generally shift towards product side or right side. Okay, so chemical equilibrium is shifting towards product side, whereas in the few cases, let us take the decomposition of the ester in aqueous medium. So in that cases, what happens? Chemical equilibrium is remains towards the reactant side. Okay, chemical equilibrium is remains towards the reactant side. Okay, so it will be right side or left side. But it won't tend to complete. Okay, these reactions won't tend to complete. But practically what we are saying, reactions are completed. So that's why what we can say, generally opposing reactions do not proceed to completion. Opposing reactions do not proceed to completion. Okay, opposing reactions do not proceed to the completion. Okay, so in this case, if you take the overall rate or net rate, okay, so overall rate or net rate is influenced by the forward reaction. Okay, so here we have the two reactions, one is the forward reaction and another one is the backward reaction. So if you take the net rate of the reaction, it is generally influenced by the rate of forward reaction as well as the backward reaction. And if you take the progress of the net reaction, it is generally decreases. Okay, it is generally decreases and ultimately becomes zero at the equilibrium point. Okay, the net rate of the reaction is ultimately becomes zero at equilibrium point. Okay, equilibrium point. Okay, yes, so that's why if we take the characteristics of the reactions, so first one is what we can say. So tell me characteristics. Here we are taking the characteristics. So here first one is. So if you take the first characteristics, what we can say? These opposing reactions. Okay, these opposing reactions. Otherwise, in opposing reactions, simple reactions takes place simultaneously and opposes with each other. Okay, simple reactions takes place simultaneously and opposes one another. That is the first characteristics. Okay, so takes place simultaneously and opposes. Okay, and opposes one another. Okay, opposes one another. It is the first characteristic. Second one is, so in opposing reactions or reversible reactions, products have the chemical affinity. Okay, generally products have the chemical affinity. That's why they are reacting and giving the which one? Original reactants. Okay, so that's what you are saying. In opposing reactions, products have the chemical affinity. Okay, so products have chemical affinity. Products have chemical affinity. Chemical affinity. Affinity. Third one is, so where the chemical takes place? So generally the chemical takes place in chemical equilibrium. Okay, so that's what we are saying. Opposing reactions are occurs in chemical equilibrium. So the third one is occurs in chemical equilibrium. Chemical equilibrium. Chemical equilibrium. Fourth one is what we can say, these opposing reactions are do not proceed to completion. Okay, opposing reactions are do not proceed to completion. Okay, so do not proceed to completion. These opposing reactions are do not proceed to completion. So next point is, if we plot a graph between the concentration. Okay, so if we plot a graph between the concentration and time. Okay, if we plot the graph between the concentration and time, it seems that the concentration of the reactant gradually decreases. Okay, the concentration of the reactant gradually decreases, whereas concentration of the products are gradually increases. Okay, so reactant will be what happens, decreases, and product concentration will be increases, but after some time both will become constant. Okay, both will become constants. So that's why here what we are doing, we are plotting the graph. Okay, so we are plotting the graph. Okay, so here we have to plot the graph. So let me plot the graph between the concentration and time. Concentration and time. So what will the plot we can get? Let me see. So now you have to take the concentration and time. So generally concentration is taken on the x axis. Concentration is taken on the which axis? Y axis. So here we are taking the concentration. So concentration is taken on the y axis, whereas time is taken on the x axis. So if you do like that, so the concentration of the reactants gradually decreases and becomes constant. After some time it becomes constant. Whereas if you take the product, so initially we don't have the product, so its concentration is 0. But after some time we have the products, so their concentration will be increases, and later it is also becoming constant. Okay, it is also becoming constant. So this is the product concentration. This is the reactant concentration. So these are the plots. Okay, yes. So next one is, so instead of the concentration, what you have to do, take the rate of the reaction and percentage of the products. Okay, so next plot is, in the next graph case is what we are doing, we are plotting the graph between the rate of reaction and percentage of products. Okay, rate of reaction and percentage of products. Rate of reaction and percentage of the products. So here percentage of the products. We are taking the percentage of the products, and here we have to take the rate of reaction. Rate of reaction. Rate of the reaction. So initially, if you take the rate of the forward reaction, so what happens? It is gradually decreases. Okay, rate of forward reaction decreases gradually. Whereas if you take the rate of the backward reaction, so it is increases. It increases. It increases gradually. Okay. So this forward rate and backward rate both will be coincide at a point. So this point is called as equilibrium point. Equilibrium point. Equilibrium. Equilibrium point. Okay, equilibrium point. Okay, so equilibrium point means the point at which the rate of the forward reaction and the rate of the backward reaction both will be same. Okay, both will be same. So that point is called as equilibrium point. Okay, that point is called as equilibrium point. Otherwise, the point where the net rate of the reaction becomes 0. So that point will be called as equilibrium point. Okay, so in other words, what we are saying, the net rate of the reaction will become 0 at a point. That point is called as equilibrium point. Okay, so this is about equilibrium point, and it is the A, and assume this is the B, and it is the C, and this is the D, whereas this is origin. Okay, so this point is assume E, so E is the equilibrium point. Okay, so from this graph, what we have to assume? So there, first one is what you can say, the rate of the forward reaction decreases gradually. Okay, that's the one point. And second one is, so in first case is what you are saying, rate of forward reaction decreases. So decreases. Forward reaction decreases, and second case is the rate of the backward reaction increases. Increases. Okay, the rate of the backward reaction increases gradually. And third one is at equilibrium point, the net rate of the reaction is 0. So that is dx by dt is equal to 0. Okay, dx by dt is equal to 0. So these are about the important characteristics of the opposing reactions or reversible reactions. Okay, opposing reactions are reversible reactions. So now we have to take the reaction kinetics. Okay, reaction kinetics. So let me take the reaction kinetics. Reaction kinetics we have to take. Okay, so reaction kinetics. Now we are taking the reaction kinetics. Reaction kinetics. Reaction kinetics. Okay, yes. So now we are going to take the reaction kinetics. So now we have to take the reaction kinetics. Okay, so if you want to take the reaction kinetics, so there we should assume have the two conditions. Okay, so before taking this reaction kinetics, what you can say, we may have the two conditions in these opposing reactions or complex reactions. So first case is when both the reactions are have the same order. Okay, so when both the reactions are of same order. Okay, so first case or first condition is when both the reactions are of same order, and second one is when both the reactions are of different order. When both the reactions are of different order. Okay, first case is the forward reaction as well as backward reaction. Both have the same order. So it may be zero order, first order, or second order, or third order, whatever it may be, nth order. Okay, yeah. In the second cases, the forward reaction and backward reaction both have the different order. Okay, so that is the condition. So now you also we should take the first one. Okay, so we are going to take the first one. So that is the when both the reactions are of same order. Okay, both the reactions are of same order. So in order to reduce the rate equation, we should assume both the forward and backward reaction are of first order reactions. Okay, so what we are assuming, the forward reaction and backward reaction both are of first order. Let us take an example. Consider the reaction A is converting into the B. A is converting into the B. Okay, so here A is the reactant, it is converting into the B. After some time, B is coming back into the original reactant A. That's why it is the reversible reaction. Okay, it is the reversible reaction. So here we have the rate constant. One is K1 and another one is K2. So here what we can say, where K1 is which one? First order rate constant. Okay, so first order rate constant it is, otherwise first order forward reaction constant. Okay, simply you say first order rate constant. It is the forward reaction only, so it is the first order rate constant, and A2 is first order rate constant of backward reaction. So it is also first order rate constant, first order rate constant of backward reaction. First order rate constant of backward reaction, whereas first one is first order rate constant of forward reaction. Okay, one is the backward reaction and one is the forward reaction. Okay, otherwise forward reaction and backward reaction. So both are opposing one another. Okay, both are opposing one another. So this is the condition. Okay. So now just you assume the initial concentration of A and B should be small a and 0. Okay. So we are taking this reaction and assuming that the initial concentration of reactant A is small a and the initial concentration of product B is 0, because reaction is going to start. So that's why its concentration is 0. Okay. So after some time what happens? Assume X moles per liter of the A will be transforming into the which one? B. Okay, so it is transforming into the B. So if you take the concentration of the A and B after time t, then what happens? A concentration is A minus X, whereas B concentration is X. Okay, so A concentration is A minus X and B concentration is X. Whereas if you take the concentration of A and B at equilibrium, so at equilibrium, reactant A concentration is A minus Xe, whereas this product B concentration is Xe. Okay, so that I have to indicate here. So initial concentration. So initial concentration. So initial concentration, if you take initial concentration, so reactant A concentration is A moles per liter, whereas B concentration is 0. And after time t, if you take the A concentration, what it is simply A minus X moles per liter. moles per liter. Whereas if you take the B concentration, it is X moles per liter. Moles per liter. X moles per liter. So at equilibrium, if you take the A concentration, it is A minus Xe moles per liter. Moles per liter. Whereas B concentration is X E moles per liter. X moles per liter. So this is about the concentration of reactant A and product B. Okay. So now what we have to do? Just we have to take the rate of A. Okay. So just we have to write the equation for the rate for A, reactant A, and rate for the B. So if you take the this rate of A, so it is simply minus. Yeah. Otherwise, what you can say, the rate of forward reaction. Okay. So the rate of forward reaction. So minus dA by dt. The rate of forward reaction minus dA by dt is equal to what we can write? K1 into A minus X. It is simply K1 into A minus X. Okay, A minus X. Whereas next one is the rate of backward reaction. Rate of backward reaction. How can we write? So it is simply dB by dt is equal to K2. So rate constant. Okay. Backward reaction. So K2 into X. Okay. K2 into X. So this is about the rate of backward reaction. So now we should take the net rate of the reaction or overall rate of the reaction. So the overall rate of the reaction is equal to the rate of forward reaction minus the rate of the backward reaction. Okay, the rate of the forward reaction minus the rate of the backward reaction. So that's why how can we write the net rate of reaction? The net rate of reaction. The net rate of reaction that is indicated by the dx by dt is equal to what it is. So we can write minus dA by dt minus dB by dt. So dB by dt. Okay, so just we have to substitute these values. Dx by dt is equal to, it is minus dA by dt is equal to, how can we write? K1 into A minus X. K1 into A minus X minus the rate of backward reaction is K2 into X. Okay, K2 into X. Also, this is the equation 1. Okay, that is the equation 1. Okay, so yes. Just you have to copy these things. So I am erasing it. So let me see what happens later. So next, how can we write? So where we have to take the condition or equation. Okay. So next one is at equilibrium. So at equilibrium, dx by dt is equal to 0. Okay, so simply it is dx by dt is equal to 0. So therefore, how does it becomes? 0 is equal to, and in this case, you should substitute the equilibrium concentrations. So that's why it is K1 into A minus Xe minus k2 into xe. Now bring this k2 into xe to the left side. So it is k2 xe is equal to k1 into a minus xe. Okay, k2 xe is equal to k1 into a minus xe. Now just you take the k2 value. So k2 is equal to k1 into a minus xe by xe. Okay, so by xe. Assume this is the equation 2. Okay, so this is the equation 2. So further, how can we simplify this? So further, how can we simplify by this one? So it is simply k2 xe is equal to k1 a minus k1 xe. So like this you can write. So later k2 xe is equal to, how can we simplify further? Yeah, how can we simplify? Just what I will do here, bring the minus k1 xe to the left side. So if it comes to the left side, it will become positive. So plus k1 xe. K1 xe is equal to k1 ea. So here which one is the common? xe is the common. So take it as the common factor. So we are taking common. That's why it is k1 plus k2 into xe is equal to k1a. K1a. Later, how can we write that? Yeah, how can we write? Simply just what we can do? Yeah, take the k1 plus k2. k1 plus k2 is equal to k1a by xe. So assume this is the equation 3. Okay, it is the equation 3. So k1 plus k2 is equal to k1a by xe. Okay, k1a by xe. k1a by xe. Now we have to substitute the equation 2 in equation 1. Okay, so equation 2 in equation 1. So substitute equation 2 in equation 1. Equation 1 is which one? Dx by dt is equal to k1 into a minus x minus k2 into x. So k2 value is k1 into a minus xe by xe. So that we have to substitute. So it is simply k1 into a minus xe by xe into x. Now simplify it. So here xe is LCM. Okay, so take the LCM. So it is simply xe. So dx by dt is equal to xe k1 xe into a minus x minus k1 into a minus xe into x divided by xe. Okay, now again you have to simplify. Here just you have to multiply all the things. So k1 xe into a minus k1 xe into x minus k1 x a minus into minus plus k1 xe x divided by xe. So it is dx by dt. Okay, so further, how can we simplify? Here minus k1 xex, here k1 xex. So both will be cancels. Remaining one is k1 xe and here minus k1 xa. So both the cases k1a is common. So take it as the common k1a into what it is xe minus x divided by xe. Okay, so this is about the dx by dt. Now what you have to do? Send this xe minus x to the left side. So it is dx by xe minus x is equal to k1a by xe into dt. Now we should take the integration on the both the side. Now we have to take the integration. Okay, let me take the integration, then see what happens. Okay, so integration of dx by xe minus x is equal to, so here k1a by xe is common. Okay, yeah, so it is k1a by xe is common, and it is a constant value, so that's why we are keeping inside. So that's why later it is integration of dt. Okay, so how does it? Integration of 1 by x dx. Okay, integration of 1 by x dx is equal to minus ln x. So that's why here it is minus ln xe minus x. So is equal to integration of constant, it is a constant only, k1a by xe. Integration of dt, it is t, plus we have the integral constant. Okay, so it is the equation 4. So here I is equal to integral constant. I is equal to integral constant. Okay. So now we just assume t is equal to 0. Then if t is equal to 0, that means we didn't start the reaction. Then x is equal to also 0. Okay, x is also 0. So that's why what does it becomes? Minus ln xe minus 0 is equal to k1a by xe. T is equal to 0 into 0 plus I. So now what we can get? We can get the I value. So minus ln xe is equal to I. So it is the equation 5. Now substitute the equation 5 in equation 4. So substitute equation 5 in equation 4. Then what can get? Minus ln xe minus x is equal to k1a by xe plus, yeah, here we have the minus value, minus ln xe. So now you just bring the minus ln xe to the left side, then it will become positive. It will become positive value. So that we have write there. Okay, write it. Minus ln xe minus x plus ln xe is equal to k1a by, it is the k1a by xe into t. Now how it is? Log a minus log b. Log a minus log b is equal to log a by b. So write that. So it is simply ln xe by xe minus x. Log a by b. So xe by xe minus x is equal to k1a by xe t. So it is the equation 6. So further we have the k1a by xe value. It is k1 plus k2 only. Okay, so that's why what you can say that is yes, from equation 3 and 6. How does it becomes? How can we write this equation? Ln xe by xe minus x is equal to k1 plus k2 into t. So this is the equation 7. If we want to further simplify it, so it is simply how can we write? kt is equal to kt is equal to 2.303 log xe by xe minus x, xe by xe minus x. So this is equation 8. So here k is equal to overall rate constant, overall rate constant. So its value is which one? Which is nothing but k1 plus k2 only. Okay, k1 plus k2. Yeah, k1 plus k2. So t is the time. Okay, this is the time. That's it. Okay, so this is about the which one? Integral equation for the opposing reaction or reversible reaction. When both the forward and backward reactions are first order reactions, then we should take this equation. Okay, so now we have to calculate the TF value. Okay, next one is half-life of reaction. Half-life of reaction. Half-life of reaction. Half-life of reaction. The minimum time required to become initial concentration of is called as half-life of reaction, or in other words, the time where the initial concentration of the reactant becomes half is called as half-life of the reaction. It is generally denoted by T of. It is generally denoted by T of for first order reaction, for first order reaction, for first order reaction, T of is equal to 0.693 by K. Okay, for first order reaction, the half-life of the reaction is equal to 0.693 by K. So where K is equal to first order rate constant. K is equal to first order rate constant. Let us assume the effective half-life or overall half-life or net half-life of the reaction is denoted by T, and its overall rate constant is denoted by K. Then its half-life T is equal to 0.693 by K. Okay, 0.693 by K, where T is equal to overall half-life, overall half-life, overall half-life or effective half-life or net half-life of the reaction, and K is overall rate constant, overall rate constant, overall rate constant. Okay, overall rate constant. For opposing reactions, for opposing reactions, the overall rate constant K is equal to K1 plus K2. Okay, overall rate constant K is equal to K1 plus K2, where reactant A is converts into the B. After time converts into the A. So its rate constant is K1. K1 is the first order rate constant for the formation of B from A, and its half-life T of is equal to T1, and K2 is first order rate constant for the formation of product A from reactant B, and its half-life T of is equal to T2. Then T1 is equal to 0.693 by K1. T1 is equal to 0.693 by K1, and T2 is equal to 0.693 by K2. Okay. K2. Assume this is the equation 1, and this is the equation 2, and this is the equation 3. It is equation 3. This is equation 4. Okay, equation 4. Now substitute equation 3 and 4 in equation 2. Substitute equation 3 and 4 in equation 2. Then what happens? So equation 2 is the which one? K, overall rate constant. K is equal to K1 plus K2. How can we get the K1 plus K2? So here K1 is equal to 0.693 by T1. Okay, so 0.693 by T1 plus K2. It is a K2. So K2 is equal to 0.693 by T2. Now among these two, 0.693 is the common. So take it as a common factor. So on taking it as a common, 0.693 into 1 by T1 plus 1 by T2. 1 by T1 plus 1 by T2. This is the equation 5. Okay, assume it is the equation 5. Now compare the equation 1 and equation 5. Equation 1 and equation 5. So from the equation 1 we can get the k value. So both are the k values. So on comparison from equation 1 and equation 5, how does it becomes? How does it becomes? Simply it is this one, 0.693 by which one? Into, assume it is the into, take it as a common. We have taken it as a common factor. So into 1 by T1 plus 1 by T2 is equal to 0.693 by T. So in this equation 0.693 is the common. So both will be cancelled. The remaining one is 1 by T1 plus 1 by T2 is equal to 1 by T. So this is the final equation used to calculate the effective half-life of opposing reactions or overall half-life of the opposing reactions. Now I will stop here. Later we will continue.